So number one says we're looking at f of x equals absolute value of x. If you're like me, a real visual person, and you just want to look at it, I will draw us a picture. Which of the following statements about f are true? So the first one is function is continuous at 0. And yes, we can trace without lifting our pencil off the paper. So we are continuous. Actually, the whole graph is continuous. F is differentiable at 0. So that's where we have a problem. We have that sharp edge, so not differentiable. And then 3 is f has an absolute minimum at 0. And yes, that is the lowest point down on the graph, so that is the absolute minimum. And so we get Roman numeral 1 and 3, which is D. All right, second one, we have this piecewise function. Again, which of the following statements are true? So we're going to have to go through each of these. So limit as x goes to 3 exists. We're going to have to look from the left and from the right. And basically all you're going to do is plug in 3 to each of these and see if they come out to the same thing. We're seeing if the two pieces link up, which means are both sides coming to the same value. So if I plug 3 in for the first piece, I'm going to get 5. And if I plug 3 in for the second piece, 12 minus 7 is also 5. So the limit is going to exist. Both sides are headed towards the same place. All right, so is the function continuous? Yes. I just saw that I got 5 for both of those, so that means the two pieces are going to link up. And so the graph is continuous there. But are we differentiable? Now you need to look at the slopes from each side. We're going to be able to avoid having to do all those limits because both of these pieces of the function are linear. So I can just go by the slopes. If you have something that's not linear, you would have to actually go through the whole limit process and do the derivative. But if they're linear, we can just use the slope. So the slope from the left side is going to be 1, and the slope from the right side is going to be 4. So those are not matching up. So we're not going to be differentiable there. The slopes for each side are not the same. So we get Roman numeral 1 and 2, which is D. These Roman numeral questions are tough because you have so much that you have to look through. You have to look through all of the Roman numerals for each of them. All right, here we have this beautiful graph. It says, at which value of x is the function continuous but not differentiable? And so that would be here at A. The graph is continuous. You can trace it without lifting your pencil, but it's not differentiable because of the sharp edge. So that one. All right, 4, we have this function. It says, what is the value of the derivative at 3? Again, I like a picture. So I'm going to go ahead and draw one. This is the absolute value graph moved right 3 and up 2. So I'm going right 3 up 2. Here's my absolute value graph. And it says, what is the value of the derivative at 3? Well, at 3, we have this sharp edge, so we can't get a derivative there. So that is E, non-existent. We cannot get a derivative at that sharp edge. All right, 5, we've got another interesting graph here. I'll zoom in on it. It says we have a vertical tangent at 2, and we have horizontal tangents at 1 and 3. And it says, for what values is the function not differentiable? So I'm just going to kind of go left to right. We would not be differentiable at 0 because we have a jump discontinuity there. So definitely 0. And then we would also not be differentiable at 2 because of the vertical tangent line. Horizontal tangent lines are fine. That slope is 0. The reason vertical isn't okay is because that slope is undefined. So that's why we can't get a derivative there. It's, by definition, it's undefined. So 0 and 2, which is B. All right, so 6, let f be this function defined above, this piecewise function. Which of the following statements are true? So again, we've got to go through all of these. F has a limit at 2. All right, well, let's try to find one. Let's try to do the limit as x goes to 2 and just sort of see what happens here. Now, if we try to plug in 2, we're going to get 0 over 0. So I am going to need to factor that. And then the x minus 2's are going to cancel. And if I plug in 2, my result is going to be 4. So we got a limit. There is a limit. We got 4. We didn't get does not exist or anything. So there is a limit as x approaches 2. Now is the function continuous at 2? So remember your rules for continuity. There's a point, there's a limit, and they equal each other. So our limit is 4, but it says that the actual point when x is 2 is at 1. So we have a situation like this where this graph was approaching 4, but they plucked that point out and stuck it down here at 1. So like this was our graph and that point should have been there, but we took it out and stuck it somewhere else. So you're not going to be continuous. There is a point and there is a limit, but they're not at the same place. And then Roman numeral 3 says function is differentiable. Well, if the function's not continuous, then it can't be differentiable. So we get only Roman numeral 1. So that one is A. All right, number 7. At x equals 3, this function is, and then all your choices have to do with being continuous and differentiable. So let's check if the function is continuous. I just want to see if the two pieces meet up. So I'm going to plug 3 into both of them. So for the first piece, I will get 9. And for the second piece, if I plug in 3, 18 minus 9 is going to be 9. So we are continuous. And then we need to check if we're differentiable. From this side, our slope is 6. For the other side, we're going to have to do a limit. This is not linear, so I can't just look at the slopes. I'm going to have to actually do this limit process. So it'll be limit as x goes to 3. That's our x value. And then it is the function. So it is x squared minus whatever you get when you plug in 3, which I already did. That was 9. And then this will be over x minus 3. And I'm going to have to factor that. So that will split x plus 3, x minus 3. And so the x minus 3's are going to cancel. And if you plug in 3, 3 plus 3 gives you 6. So the slope, or the derivative, from the left side is 6, and the slope from the right side is also 6. That's really kind of rare for them to be able to match up like that, but they worked this problem in such a way that they both came out to 6. So we are both continuous and differentiable, which is really kind of rare for a piecewise function to meet up perfectly like that, but they made sure this one did. So that is. All right, and then last one, if the limit as x approaches a of some function is L, and L is a real number, which of the following must be true? A limit does not really guarantee you much of anything. All a limit tells you is that the graph approaches that value. So what this means is for this A value, the graph is approaching L on both sides. So it's doing something like this. But I don't know if there's actually a point there or not. There could be a point somewhere else. So I don't think we're really going to get much out of this. F of A exists. Yeah, not necessarily. There could be a hole. F is continuous. Again, there could be a hole, so not necessarily. Function is defined there. Maybe not. F of A equals L? Well, maybe not. Maybe it equals something else. Maybe I have a point up here. So we get none of those. A limit doesn't really guarantee you anything except behavior. Just both of the sides are approaching the same place. That's the only thing it guarantees you. It doesn't tell you that there's a point or that you're continuous or anything else, just that both sides come to the same place.